would like to thank the organizer of this mini symposium for nice opportunity to discuss results that were conducted during around 10 years in fruitful collaboration with Institute of Mechanics and Mechanical Engineering, ENSEMBLE in Bordeaux. And I would like to outline my talk. I would like to discuss as there is or not a real physical mechanism responsible for crack initiation in the bulk of samples, and what mechanism could be related to specific nonlinear aspects due to the nonlinearity of free energy release, because similar tendencies we found more than 30 years ago between Greek conditions. And in the second part of my talk, I will try to discuss scaling laws for damage kinetics and similar solutions concerning damage accumulation that will be linked to fissure initiation and crack propagation, and some links between stages of damage failure transition and morphology. That was the subject of our discussion. I would like to attract your attention to emphasize again concerning this long-term discussing subject concerning the saturation effect of Gigacycle. And I'm very sensitive to the remarks by Mugrabi, okay, that very high selectivity failure reveals the sharpness of the solution of fundamental problems of damage failure transition at all, not only concerning fatigue loading, concerning characteristic stages of damage localization, how it links with crack initiation, and how its typical situation for very high cyclic fatigue, damage control crack propagation, related of course to the understanding of nature of scaling laws, including Paris law, that could be generalized for very high fatigue. And of course, one of the key questions, what could be the mechanism of initiation of crack with specific pattern like fissure that in the bulk of the specimen? Is it really related to some artificial intrusion, or behind that some physical mechanism? For introductory reason, I would like to pay attention, to attract your attention to characteristic pattern during fatigue related to multi-scale persistent bend evolution when we have transformation in dislocation substructures with pronounced mechanism of saturation also, because we have change of dislocation density and spacing between characteristic structure, and similar results were obtained also in Russia when it was found very pronounced bifurcations in terms of characteristic density of dislocation that exactly correspond to this pattern. To come back to the possible nature of crack initiation in the bulk of the sample, I would like to attract your attention to our experimental and theoretical results that were obtained around 30 years ago when we investigated in situ different stages of damage evolution in creep condition for the sample, combined in situ with small angle X-ray diffraction that allowed for different time to estimate spatial distribution of defects. It's a fatigue, it's a creep dependence, characteristic time of failure versus applied stress, and it was found that defect density distribution in this linear portion of slope every time its well-known case corresponds to the nucleation of cracks at the near surface area. But it was established also when we are going to approaching to some limit, and when we incite of some characteristic area, you can see that hot spot of damage localization in the bulk of the sample. In parallel, it was developed field description for this phenomena, and the background of this field description, it was a result also from the in situ observation of characteristic defects in Greek condition concerning characteristic size, concentration, and it was obvious for us, but it was of course linked with some another area of activity because it's very important also for the prediction of shock material behavior. It was developed statistical theory of typical defects with corresponding modes. It was developed generalization of statistical theory for out of equilibrium system, concerning generalization of body depth statistics. And it was a realized procedure of the averaging, microscopic variables related to microcracks or microshears, with the goal to obtain constitutive law for defect density tensor, its deformation induced by defects. And it was found that only single parameter related to structure dramatically influences on the evolution of this parameter, and this parameter represents the ratio to scale, characteristic size of defects and spacing between defects. When this equation was solved, it was found that there is two characteristic critical points in terms of this delta parameter when we have very pronounced bifurcations, and this bifurcation is related to different mechanisms of structure-induced relaxation. For instance, this metastability area corresponds evolution of dislocation substructure that I mentioned after oral papers. But if we pass some characteristic scale, we have new bifurcation with infinite jump, and corresponding nonlinearity was reflected to in the form of out of equilibrium free energy release in terms of these parameters. And it was derived equation for these field variables, and study of characteristic nonlinearity of group properties of this equation allowed us to establish that there is two types of similar solution related to metastability area, its solitary weight, with the front corresponding to multi-scale transformation in dislocation substructure. But if we pass some another critical point, this structure, this similar solution is transformed in specific similar solution with blow-up nature. It means that over the scales, that is the characteristic value in self-similar solution, we have blow-up region. And these results were used to explain scenario of interpretation of experimental data in typical experiment for gigacycle fatigue. I don't know what happened, but most important picture disappeared. Yes. But, it's we investigated for very high cycle, for gigacycle fatigue, the morphology of titanium samples with fine grains for the stability. And of course, we revealed characteristic pattern related to fisheye, MGA area, and the area for correct propagation. And we decided, since we discovered similar solutions for kinetics of crack initiation and crack propagation area, we decided to establish there is links between cell similarity in characteristic solution that was established theoretically and a real scenario and real morphology in terms of the scaling characteristics. Yes, because for instance this front corresponds this transformation in dislocation substructure, and when we have final refining, when this relaxation mechanism will not appear, we will go to dislocation free grains And these dislocation-free grains could produce the structure with the ultimate grain refinement. And using well-known technique concerning correlation function estimation, we have used results of precise morphology after interferon profile of new view. We investigate characteristic areas in terms of correlation of defect-induced roughness for FGA area and the area of propagation. And you could find for different areas, we have different Hurst exponent. That exactly, but there is scaling according to defect-induced structure, which is different for FGA area and the area of correct propagation. It's technique of the processing. And it was very important for us because there is open question how to modify Paris law for typical high cyclic fatigue area with very pronounced scaling phenomena at the power in the delta K. That is fantastically deep results for the case of small cracks. And since we have knowledge about characteristic scale of universality in scaling that was estimated experimentally, and since we understood that this character of crack propagation has intermediate asymptotic character, we derived equation for small fatigue crack growth that qualitatively is similar to the Paris-Herbert law. I recall you that it's very good correspondence for small cracks when we have this representation. But of course, due to the limitation of our resolution, because it was new view, we obtain this value that exceeds Burger's vector, but the structure is the same. It means that this scenario for small crack that is controlled by correlated behavior of dislocation substructure at the crack tip corresponds to this, and then we could jump in the areas that correspond for long cracks. I would like to attract your attention that this kind of the similarity that close to Paris law in terms of the delta K for high cyclic fatigue reflects very strong power of collective behavior of defects at the crack tip area, because similar structure we have, for instance, if we have shock wave loading of materials, metals, for different intensity, and estimation of the slope of this plastic branch every time gives 4 power or close to here. It means that collective behavior of defects at the crack tip area, due to the very high coherent behavior, could provide some similar properties that could subject crack dynamics like in the Paris law. It's my conclusion. Similarity between the kinetic of damage value transition and creep and high Gigacycle loads was established. The stress decrease leads to replacement of damage localization area from the near surface area to the bulk of the cell. Non-local damage kinetics, due to the non-linearity also free energy release, allow the description of replacement of damage localization area from the near surface area to the bulk of the center. The crack and fisheye initiation is a consequence of blow-up subsimilar solution of damage localization kinetics. The morphology of fisheye area and crack propagation area is characterized by different scale in the Hurst exponents related to different similarity law of damage kinetic. Specific feature of Gigacycle fatigue failure is the link of nonlinear damage kinetic with crack fisheye initiation and crack propagation kinetic that can be interpreted in terms of similar solution of non-model damage kinetic equations. Thank you very much.